Dr. Heather Goldstone. She is the Chief Communications Officer for the Woodwell Climate Research Center. A little, very quick background. This is what I've learned about Heather. Fell in love with the ocean as a child, and then went on to pursue marine research and really discovered a passion for communicating science. Award-winning reporter, featured in media and publications, and a lot of us know you, of course, from the WGBH show that you created, the Living Lab Radio, which I heard many times. So the message today, Heather tells us, is that when you frame climate change as a purely technical problem or a solution, you can overlook the potential of marrying technology with nature, and the benefits for a natural solution combined with technology have a big implication for the Cape and beyond. So I think with that, if I'm accurate on all that stuff, I'll throw it over to Dr. Goldstone.
Great. Thank you so much. And it's wonderful to be here with you this morning. Would love to be able to kind of meet and get to know each of you, and maybe we'll have time for that later. But I think Steve's introduction, very accurate. I come from an ocean science background. That's what brought me to Woods Hole. I've been here for just over 25 years. Got here and never left. Can't imagine a place that I would love to live more than Cape Cod. But my career has evolved, and after spending 10 years as a journalist and doing a lot of reporting on climate change, coming to Woodwell Climate to lead communications has kind of felt like coming full circle from science through communications, bringing those both together and being able to focus on the climate issue full time. And I have to say this message that Steve kind of previewed for you, the importance of making sure that we fully and fairly account for nature when we're thinking about climate change, is something that I've really learned over my past 2.5 or so years with the center. And this being the tech council, the tech sector is all about disruption. I was talking with Steve, and I thought maybe what we can do is just kind of try to disrupt a little bit of the prevailing way of thinking about climate change and see what that opens up. So with that, can everybody see my slides? And hopefully you're seeing the full screen version, not the notes version. Is that
Yep.
accurate?
Yes.
Yep, looks great.
Great.
All right. Well, check one for tech working this morning. Okay. So and as Steve said, I am with Woodwell Climate Research Center. For some of you, we may be more familiar as the Woods Hole Research Center. We were founded as Woods Hole Research Center 35 years ago. In 2020, in the midst of the pandemic, we changed our name and rebranded. And what you're seeing in this picture here is our founder, George Woodwell. That's part of the name there, cutting the ribbon at our very early pandemic rebrand launch. This was a fabulous ceremony that consisted of the 3 people you see here: George Woodwell, our then president Phil Duffy on the right, our then chair of the board Joe Mueller on the left, everybody masked, myself, and 2 camera folks there. And that was the extent of the ceremony we were able to have. We of course shared it with our community via video. But so we changed our name in 2020 to Woodwell Climate Research Center to honor George and the vision that he set out for the center, and to make it clear that climate is really what we're focused on. And George very specifically was not just focused on climate change, but specifically what he calls biotic systems, what I'll call natural systems or nature, but basically living systems and the role that they play in climate. So to zoom out from that picture, this is the Woodwell Climate Campus. We're right on Woods Hole Road as you're driving down toward Woods Hole Village from downtown Falmouth. We have 8 acres, much of which is forested and held as conservation land. We strive to be self-sufficient in our energy production and use. So you can see the solar panels on the roof and the wind turbine out in front. But going beyond simply that kind of calculus of energy, George, when we purchased this land and this historic, it was an inn, and before that an estate, this historic property, really felt that it needed to be beautiful, comfortable to work in, and experimenting with different ways of interacting with nature, that it should be an example of what we should be striving for. So you can't see a lot of it on this slide, but toward the front, this is a picture where our front yard has actually been mowed. If I'm looking out my window right now to the front, it's actually about 5-6 feet high in grasses and wildflowers coming to the end of their season. We don't mow it, or don't mow most of it for the summer and into the fall. There are also some things that look a little bit like solar panels down on the ground. Those are actually an experimental system for extracting water from the air, which should be very easy today. But is an experimental system. The idea being that systems like this could be deployed around the world to use the processes of evaporation and condensation to actually pull water from the air in places where drinking water is limited in supply. So it's an interesting campus where we're trying to experiment with and think about what we need to be doing moving forward. Before I go on, I do want to acknowledge that I think all of us are living and working on the traditional and sacred land of the Wampanoag people, very much obviously still a part of our community with their history, their language, which is wonderful in revival, and their traditional ways of life and culture and knowledge that we can bring to bear on the climate issue. And I think that's a really important thing to ground us in, thinking about how long people have been in the places where we currently live and work, and how our ways of life have changed. Because if we really think about the situation we're in with climate change, it's that long history of human civilization that really drives home the crisis that we are currently in. So what I'm showing here is a graph of temperatures, average global air temperatures over the last 2,000 years. This is from the most recent UN climate report, and they state in that report that human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. But they also have this little blue-gray bar over on the left that shows the range of the warmest temperatures over the last 100,000 years. And you can see that we are already outside of that. So if you think about climate within the context of the history of human civilization, we are already outside the temperature bounds. Just to really drive that home, if we go back even further than that 2,000 years of temperature, and here we're actually looking at inferred carbon dioxide concentrations in the air. This is calculated from drilling down through ice in glaciers and ice sheets, and examining the air bubbles in that ice that was trapped in that ice when it was formed to find the level of carbon dioxide that was in the atmosphere. And what you can see is that over a 10,000 year period, yes, there have been wobbles. Yes, there may have been a slight increase, but it's really not until we get to about 150 years ago that we see this very dramatic increase. And if you think about what's happened over the course of 10,000 years, that of course is the beginnings of agriculture, the beginnings of urbanization, really the foundations of life as we currently know it. And you've probably encountered the idea that, well, climate has always been changing. And it is true that our climate has gone through quite dramatic fluctuations, or I should say the planet's climate, because the point is really that even during the evolution of human beings, if we go back some 250,000 years ago, 500,000 years ago, right, we are seeing pretty dramatic fluctuations in carbon dioxide levels, but none of those compare to what we have seen since the onset of burning fossil fuels in terms of the change that we have had. So this is really an unprecedented climate situation in the evolution and history of human civilization. And what we have already done with the warming that is already in place is we have left behind the stable climate that has fostered the development of human civilization as we know it today. And I know that can seem like a very hyperbolic statement, but it really, just those three graphs that I just showed you, it really is true. This relatively stable climate, while it may have been a blip in the geological history of the Earth, has been the underpinning of the development of modern human civilization. And that is what we are losing as the planet warms. So to date, we have warmed the planet just over 1 degree. It's about 1.1, 1.2 degrees in terms of global average surface air temperature. 1.5 is kind of the warming limit that has been internationally agreed through the UN process, and that is in the Paris Agreement. The Paris Agreement sets a warming limit or target of no more than 2 degrees and ideally no more than 1.5 degrees C. Unfortunately, right now, we're actually on a trajectory for more like 2.7 to 3 degrees of warming. And while that seems like a relatively small number, we can all see around us at this point the impacts of climate change. One study has estimated that I think it's 80% of the world's population has directly experienced the impacts of climate change. And that comes in the form of extreme storms, extreme precipitation events, more severe droughts and heat waves, more severe and larger wildfires. We're seeing all sorts of impacts. And you know, for a long time, those advocating to stop burning fossil fuels and stop the causes of climate change didn't really want to talk about how we adapt to these changes. But at this point, it is inevitable. We have to adapt. We are already seeing a whole range of quite severe impacts. But I think we also have to keep in mind that there are limits to what we can adapt to. And what you're seeing here on this slide is one of the ministers of a small island developing state in the South Pacific, delivering an address to the UN last year from the waters around his island, showing to drive home the impacts of sea level rise and the fact that for these small island states, climate change and sea level rise are really an existential threat. There are islands that are expected, if we continue on our current trajectory, within decades to have no habitable land for their country at all. And in fact, as far back as 2015, when I was in Paris for those UN climate talks, I spoke with a law professor from Columbia University who said, yeah, the legal profession is already thinking about this and has coined a term called nations ex situ, EXSITU, nations out of place, which have no actual homeland, which as at the current moment is one of the 4 defining features to actually have a nation. So they were trying to figure out a way to create legal standing for nations that would no longer have habitable land as a result of climate change. So really, we can't just expect to continue warming the planet and adapt to those impacts. There are limits, no matter how good our technology gets, to what, frankly, the human body and living systems can adapt to. So we have to slow down and ideally stop and reverse this warming. So how do we do that? And I think the realization of the situation we're in and asking that question, what do we need to do, can prompt a lot of anxiety. And it's kind of around that we've struggled to even express the situation that we're currently in. So having talked at you for a few minutes, I'm going to see if we can actually do a little bit of interaction here. If I just say climate, what is the next word that pops into your mind? You can put it in the chat. You can go ahead and yell it out. What's the next word? If I say climate, complete that phrase. All right. Saw a few of these come up in the chat, right? Climate change just explains or describes, is the name for the phenomenon, the fact that the climate is changing. And in fact, there was an effort a few years ago to try to change that common parlance to climate disruption, because it was felt that change conveyed something that was too slow, gradual, and kind of unidirectional, when in fact, what we're seeing is climate disruption, or in some cases, climate chaos, as extremes become more extreme in multiple directions. Climate emergency, climate crisis, referring more to the social or political situation that we are in, right? The threat that climate change poses and the need to really act on that. So if you then take a moment to reflect on what is causing, what has put us in this emergency or this crisis, what is causing the change? What is the first thing that comes to mind in terms of what's causing it? Would either of these photos be accurate for what comes to mind when you think about the causes of climate change? Right? This is definitely a large part of it, but our minds tend to go immediately to things like the energy and transportation sectors, right? And that is a huge part, right? The burning of fossil fuels is the primary driver of climate change. But thinking about it only in those terms then leads to, if we think about what are the solutions, our minds tend to go immediately to the technological fixes for those. And this focus on the technologies that are causing and the technologies that could mitigate climate change tends to fill all of our thought space, all of our policy space, our attention and energy in this space. And what we're trying to do at Woodwell Climate, and what I'm hoping to do with you here today, is shift that a little bit, because this is, like I said, this is the lion's share of what needs to be done, but it is not all of it. And it is not, if we focus entirely on the technology, we both leave behind opportunity, and we actually potentially put ourselves in a really dangerous position. So at Woodwell Climate Research Center, our mission is science for solutions at the nexus of climate, people, and nature. Really thinking about natural systems, human systems, society, and how that's all bound up with climate change, and how we create solutions that address all aspects of it. And we are a relatively small organization. We're growing really rapidly. We're at a little over 100 people right now. For most of our history, we've been closer to 50, 60, 65 people. And so the way that we really have impact is to partner with leaders and communities, finding influencers in their sphere, working with them to create just meaningful impact. But I want to go back to this climate, people, nature, and where nature fits into our thinking about climate change. So what I'm showing you here is a pie chart that you can, if you just Google global emissions sources, it's one of the first things that comes up. This is a pie chart from the EPA that shows by economic sector the sources of greenhouse gas emissions globally. And what we know at this point, and again, this is a statement from the most recent UN report, current climate change is wholly and unequivocally the result of human-caused greenhouse gas emissions. But human-caused greenhouse gas emissions are not only technologically driven greenhouse gas emissions. So 3/4 of what is there is our buildings, our cars, our industry, our electricity. That is 3/4 of what is in that pie chart. And that's obviously, we can't ignore I'm not saying we should ignore that technology piece of it, because that is 3/4 of what's causing the emissions that are warming the planet. And it's critical that we address that. And we've put a lot of effort into that. We have a lot of technological solutions, and more are coming every day. We have renewable energy, we have electric vehicles, we have incredible ways to insulate and make our buildings more energy efficient. We have alternative, ways to get around, and for that matter, we're even creating ways to get protein that looks, feels, and tastes like meat without the carbon and water footprint of meat. So what's missing from this picture? Well, there's one source of greenhouse gas emissions that is not in this pie chart, and in fact is in almost none of our carbon budgets that are used to set our emissions targets, and that's something called permafrost thaw. So permafrost, as the name implies, is perennially frozen ground, mostly in the Arctic, but also in some high latitudes. Technically, it's ground that is frozen for 2 or more years consecutively, but in some cases, it has been frozen for hundreds, thousands, 10,000 years. And unfortunately, the Arctic is warming not just at the rate that the rest of the planet is, but at 3 to 4 times the rate that the rest of the planet is. And as the air and the water around the Arctic warms, that perennially frozen ground is no longer perennially frozen. It is thawing. And what you see here in this picture is, of course, if your buildings and roads and airports are built on top of ground that is kept stable because ice is the structure in it, and that ice thaws, what you end up with is wet, soggy ground, buildings, roads, airports collapsing, sewage systems leaking, water systems being impacted, coasts eroding where they're no longer protected by that hardening from the ice. And so we're seeing really a human rights crisis in the Arctic as a result of this. But that ground, because it's been so cold, there hasn't been the microbial activity that we're used to in our soils that would break plant and animal material down. And so instead, what it has done is built up carbon over years, decades, centuries, and millennia. And at this point, permafrost holds twice as much carbon as is currently in the atmosphere. And as it thaws and microbes wake up, they can munch on that carbon and they release it into the air as carbon dioxide and methane. Now, will all of that twice as much as in the atmosphere go into the atmosphere? No, but our best estimates are at this point are that emissions from permafrost thaw by the end of this century could be on par with some of the world's largest emitting countries. So could be on par with continued emissions at our current rate by the United States. Think about that for a minute, right? Permafrost thaw could be like the US continuing business as usual through 2100. And we're not accounting for it. Why are we not accounting for it? Well, in part, it's because if you look at those two yellow bubbles on either side of your screen that represent our estimates of permafrost thaw, that's a pretty big range. And things like computer models and carbon budgets have not really been built to handle such a large range. And so because there's been uncertainty about the quantity of permafrost thaw emissions, they've generally been omitted. So why is there so much uncertainty? Well, the Arctic is a vast, cold, often for 6 months of the year, dark place to work. It can be very difficult to actually get there and collect data. So what you're seeing here, all of those blue dots, the greenish area is the extent of permafrost currently. And the blue dots are places where we have monitoring stations on the ground that are actually keeping track of things like temperature and carbon flux, the amount of carbon coming out of the ground or being sucked back out of the atmosphere by plants on the ground. And you can see that there are huge gaps. And the Arctic is not one big homogeneous area. So where we have gaps, it can be really difficult to extrapolate because it could be a completely different ecosystem in that area where we have those data gaps. So the logo in the top left here, Permafrost Pathways, is a project that scientists here at Woodwell launched earlier this year. The lead of that project, Dr. Sue Natali, actually gave a TED talk in April launching it. This project has been launched with funding through the TED Audacious project. And the goal of Permafrost Pathways is to really bring science to bear in collaboration with Indigenous communities, with policy experts to fill in these data gaps, create better computer models, and then from that also create better climate policies, both for communities on the ground to adapt and address the impacts of thaw, and for national and international government bodies to set appropriate policies that take into account this fact that permafrost could eat up as much as 40% of our carbon budget, and we have to take that into account. So we have to put permafrost thaw. We need to insert another wedge into this pie, right? But then there's this other orange 24% down there: agriculture, forestry, and other land use, which often in UN parlance just gets called a FOLU, which is completely meaningless, right? And obscures what we're talking about here, but we're talking about land and biological systems, the conversion of forests to working lands, the practices on working agricultural lands, land conversion for development, a whole host of things. That is a quarter of greenhouse gas emissions globally. Raise your hand if you would have guessed that land use was a quarter of greenhouse gas emissions globally. Yeah, I'm not seeing a lot go up, right? We know that cutting down trees has a carbon footprint, but we have not widely really integrated this idea that this is such a major part of our greenhouse gas footprint and a part of the problem. The thing is, it can actually be an even bigger part of the solution. Scientists here at Woodwell have been involved in really seminal work over the past 5 years to grapple with the question of how much could nature be in terms of a solution. And what they've come to is that if we do it right, natural climate solutions or nature-based climate solutions could provide a third of the mitigation that we need over the next 10 years. That's huge. Now, that doesn't mean we don't do the other decarbonization. Nature-based climate solutions have to be deployed in addition to, not instead of, economy-wide decarbonization. So we still need the technology. We still have to do the decarbonization. But even if we did that, if we leave out a quarter to a third, right, of the problem or the solution, obviously we're not going to get all the way there. So how is land such a big part of the problem or such a big part of the solution? And what you're looking at here is a map published a couple of years ago. This is not actually a Woodwell map. We do beautiful ones, but this is one that is showing where carbon is stored, and the different colors are showing whether it's in soil. So up in the Arctic, you see those red and purple colors. It's in the soil and the roots, and that's the permafrost that we were just talking about. And then as you move a little bit further south, you start to see the boreal and temperate forests in those slightly muted greens. And then you get down to the tropics, and there's just this blazing bright green, right? And that is tropical forests. Tropical forests are an incredible powerhouse climate solution, currently holding back a full degree of warming. If we lost our tropical forests, we would immediately and automatically warm the planet by over a degree, or at least a degree. So we would double what we've already done to our climate. So how do they do this? Well, 3/4 of that cooling effect comes from the carbon that is stored in forests. So plants essentially breathe in carbon dioxide. This is photosynthesis, right? They breathe out oxygen. And in fact, in doing that, plants and land-based ecosystems absorb about 1/4 to 1/3 of human greenhouse gas emissions each year. But what forests do that's really amazing is they lock that carbon in the tree trunks and branches. Wood is half carbon. And then they also pull that carbon and shunt it down through their roots into the soil. And in some forests, half of the carbon that's stored in that forest could actually be down in the soil. So they're a huge carbon capture and sequestration machine, essentially. You know, we're trying to develop these technologies to essentially big fans to suck carbon dioxide out of the air. Well, this is what forests are already doing on a massive, massive scale. But what we often don't appreciate is that they're also doing something else. Forests have all of these other properties in just the roughness of the tree canopy, how that interacts with the atmosphere in a physical way, the chemicals that they produce, and the water that they pump from soils through their roots up through the tree and into the atmosphere. They basically act like giant air conditioners, and through that they additionally cool the planet. So it's putting those two together, the carbon that they're pulling out of the atmosphere and storing, and this other air conditioner function that they're performing, that those tropical forests are able to cool the planet by a full degree. Now, it's important to realize when we talk about these functions that forests are doing, it's actually really important to talk about forests, not just trees, because of course, yes, it is at the tree level that we understand the physiology and the chemistry of photosynthesis and water cycling. But really, it's the forest that does this. If we think about small trees, right? If we just go out and plant 10 trees, yes, they are pulling in and sequestering carbon, but they're doing a very small amount of it. They may be doing it at a fast rate because they're growing quickly, but the size of that tree, the amount of carbon that it can hold, right, is much less than what is already stored in a much larger tree. And those intact forests are really the ones that are able to do these other cooling functions at scale. An individual tree might do a little bit of that, but it's not going to have that same impact. Those intact forests are also, of course, habitat and hotspots for incredible biodiversity. They have a host of other ecological and social benefits to them that a small stand of trees or a plantation of new trees just will not have. And so I think that's really important to realize when we think about forests as a nature-based climate solution, because there's been a lot of attention to forest restoration, to planting new trees, and that is important. But again, this is like the technology nature thing, that is important, but it cannot be instead of preserving the forests that we have. Because if we were to cut down, and we do this all the time, if we cut down large trees and then plant new trees, we often think of that as net zero, right? We cut a tree, we planted a tree. The problem is what we did is we cut one of those big trees, we released all of that carbon into the atmosphere, we decreased all of that fabulous forest function, and then we replaced it with a couple of little tiny trees, right? And it's going to take them decades to centuries to catch back up to what that forest was doing. So if we are accounting for carbon and for climate impacts on the scale of a century or more, you could probably call that net zero, but we don't have a century right now. We need to be cutting carbon now, and we need to be cutting our greenhouse gas emissions by more than half over the next 7 to 8 years. So we can't afford to put that carbon into the atmosphere and wait decades for trees to pull it back out. So protecting forests is really, really critical. But that's not the only, forest protection and forest restoration are not the only nature-based climate solutions. They're really huge ones. But I did want to touch on a couple more before I end and we get to the Q&A part of this. And that has to do with soils and agriculture, right? Obviously, feeding 8 billion people is an incredible challenge. And when we're talking about preserving and restoring tropical forests, we have to take into account the fact that that obviously comes at the potential expense of communities living in those places. And so what Woodwell has been putting a lot of effort into is working with, say, small farmers and traditional communities in Brazil, in Congo, to say, okay, what are the trade-offs? What do you need? And what we've really figured out is there's a combination of technical support to those communities to be able to produce as much or more food as they are currently producing. That's both for subsistence and also as a potential revenue source. And then they need a source of revenue. And so we need to figure out models for actually supporting these forest and forest adjacent communities in food production, as well as forest conservation and restoration. But then there's also a lot of other working lands that have already been converted from forest or from whatever they used to be to working lands. And we need to think about those because there's actually a huge amount of potential in those. And over 12,000 years of agriculture, a lot of our practices have degraded the soil and released a lot of carbon. And there's potential for us to be putting more carbon back into that soil, making it healthier soil and improving our food systems, while at the same time sequestering more carbon. And that leads me to my last idea, which is that ecosystem restoration in a lot of different places can take a lot of different forms and can be, again, both a global climate benefit and a local community benefit. So on the left, you're seeing a picture of rangelands out in Colorado, where we're working to figure out how different rangeland management practices can impact soil carbon and soil health. And then on the right here is a picture from almost literally my own backyard, but right here in Falmouth, the Coonamessett River Restoration Project, which has been an amazing project over the past 5 years to restore an abandoned cranberry system of cranberry bogs into native river habitat. And one of the really cool things about this that we've discovered is that what they did to reestablish the plant life there was not to go in and plant trees and bushes and spread grass seed and say, okay, we think this is what should be here. Instead, what they did was they dug down below where there had been impacts from the cranberry agriculture over the past 100 to 200 years, turned that soil up. And what they found was an immense diversity of seeds, native seeds that were able to germinate and create this whole ecosystem that is far more diverse, that is doing far more in the way of carbon absorption and nitrogen nutrient removal than any kind of constructed restored ecosystem would have. And so by following this very closely scientifically, what we're learning is that, you know, just taking our hands off of a cranberry bog, it wouldn't look like this. But it also wouldn't look like this if we went in and tried to do each and everything. It was this in between of creating the right conditions then for this system to reestablish itself. And so there is, I think, a really critical interplay that we need to find when we think about natural systems in a climate context, which is that natural systems, whether it's permafrost thawing in the Arctic or tropical forests, have the potential to make or break our climate targets. They really do. But nature alone is not going to solve this problem. We can't simply take our hands off and expect it to meet this full potential. And that's where technology can really come in to help us both find, I mean, those maps that I was showing you, the amount of satellite technology and computer power and science that goes into producing a global map of where carbon is stored is huge, right? So technology has a huge role in helping us find that potential and then unlock it and track it and really make sure that we are maximizing our nature-based climate solutions. So with that, I will, if I can find my stop share button, I will stop sharing and happily take any questions.
Thank you so much, Heather. I can definitely start with a question. You mentioned technology aiding the modeling and the informatics around what we can do and what we can't do. You know, Bitcoin mining has been called a threat to climate change because of the resources that compute power required draws. Love your thoughts on that. You know, we're using the tools to get to the answers, but by using the tools, is that the best way to get to the answers? I'd love your thoughts on that. And then with that, just in computer modeling, because the biological systems are so complex and there's so much variability, there'll always be a margin of error. What's the acceptable margin of error in those models? Or how do you manage that, just that there's so much to put into a model, into a computer model, and how do you simulate a real environment?
Okay, well, I'm going to leave kind of the Bitcoin side of things to the side, but I think you point out a really critical dilemma that we do grapple with on a regular basis, and that is that our work, everything that we do, has an impact on the climate. So whether it is the computing power necessary to run climate models, or whether that is the fuel cost of flying to a remote part of Alaska to install a permafrost monitoring station, or flying to Brazil or the Congo to talk with communities on the ground there about forest conservation and study those forests, that all has an impact. And we do think about that. And I think the best answer that we've come to is simply being aware of that, and not necessarily in a super quantitative way, but making the best value judgments that we can about, is this the most important thing that we can be doing in order to drive the systemic change that is needed. And so, you know, not taking flights frivolously, not running a huge computer model for no reason. I actually had an interesting conversation just last week. We were talking about attribution science, right? So the ability to take any particular weather event. If you go back 10, 15 years, when I started reporting on climate, the standard answer from any scientist in response to the question, did climate change cause this? Which, first of all, is the wrong question. Climate underlays all weather, so it is involved in all weather events. But how much worse was this event made by warmer air temperatures and atmospheric changes? The answer to that would be, well, we can't attribute any one particular weather event to climate, but this is the kind of thing we expect. And that answer has changed dramatically to where now we can run computer models after an event, go back and run the model essentially with the impacts of climate change, or assuming without the impacts of climate change, see how different the end results of those models are and say, okay, climate change made this event 15% worse or 80% more likely. Running those computer models has a huge carbon impact. And we were actually kind of brainstorming around, wouldn't it be cool if we were running those concurrently, essentially constantly, so that weather forecasters in advance of events could be telling you how much of an impact of climate change they were seeing in the forecast weather coming up, because we know that people's attention to weather is they're much more focused on weather events before and during, and by the time they're over, attention goes elsewhere. And someone said, well, that would be really cool, but that would be a doubling of the already immense computing power that goes into weather forecasting and climate modeling. And that would have a huge carbon footprint. So would it really be worth it? And I don't know that there is a quantitative yes or no answer for a lot of these, but thinking, okay, what is the value in being able to reach people with information about the climate impact on our weather in advance of a major storm instead of afterward? Is that worth the power? And we kind of went, well, maybe doing that, maybe starting it up and running it in advance of like a Hurricane Ian would be worth it. But doing it every day, maybe not worth it. And so I think it's constantly making those judgment calls and thinking about, is this the most important thing we could possibly be doing to push the world in the right direction? And if so, then go and do it. And it has an impact, but don't be frivolous about it. That's a long-winded, not very quantitative answer, but I think that's kind of where we are in thinking about it. So.
They're thinking about forests and the impact of deforestation, which can be partly a political problem or largely a political problem. Is focused also there, or is it more on kind of mitigating what's already been done to forests to try to improve that situation?
No, obviously, I mean, the tropical forests that we have right now are holding back a degree of warming. It is critical that we stop deforestation and not continue to lose those forests. And in fact, almost exactly a year ago, the first day of the UN climate negotiations last November, most of the world's national leaders declared that they were committed to ending deforestation by 2030. That's exactly the right, or I mean, sooner would be better, but that's a great goal, right? That's what we should be aiming for, is that kind of ambition and ending tropical deforestation. The problem is we've heard pledges like that multiple times before, and they don't come to fruition. And that's because we run up against social and political issues. And, I think how we've tried to approach this is to say, all right, we need to figure out win-win solutions, or at least win-draw solutions. And not set this up in a way that find a way to get around the idea that there's a dichotomy between forest conservation and development, that it's one or the other, right? And to say, and in development, I don't mean the building of cities, I mean in the sense of sustainable development and enhanced well-being, really is how we talk about it, right? We need to find ways for those communities and those countries to continue to enhance quality of life and well-being for the people who live there, and at the same time, protect those forests. And so, like I said, that for us has taken the form of really going and doing a lot of social science and work with communities in place to understand what are the needs, what are the trade-offs, and how do we start to get around those, and then start to work on those, the methods for how we get around that. So, for example, in DRC, that means that we've been working to document the effectiveness of something called the system of rice intensification, which is a different way of growing rice that allows for more production, more yield of rice without actually expanding the amount of area being used for rice production, so that people can have enough to eat, potentially have enough to sell, and start to have actually a business in addition to subsistence, and do that without cutting down more forest. in Brazil, that's been a combination of things where we have projects going essentially as experimental or demonstration projects, where it's about providing technical assistance to small landholders for things like composting on their farm to then create an inexpensive land amendment that allows them to get more yield from their land without continuing to expand through deforestation the amount of land that they're actually farming. Again, the idea to get past subsistence to potential revenue production, and then also just straight up paying small landholders in Brazil. Many landholders have an allotment. There's a certain percentage of their land that they are legally allowed to deforest each year. And so we have a project called Conserve that is experimenting with a model of paying annual payments to these farmers to not use their legal deforestation allotment, so that the forest is being protected, but those farmers are not feeling the same opportunity cost as if we just did that in a regulatory way and just said you no longer have that allotment. So there's some creative work in figuring out what are the social and financial and political structures that can help us get past some of this roadblock that comes from thinking about it as an either or. But just one last thing I will say is that clearly, yes, politics plays a huge role in all of this. And we've seen that very clearly in Brazil over the past 10 years. So if we go back 10 years, deforestation rates in Brazil had dropped and were at their lowest rates in over a decade. And that was because of years of very strong collective action based on science about the importance of the forest. There was an investment in the Brazilian government agencies to monitor forests. There was protection put in place. There was enforcement of those protections, and we saw deforestation rates drop dramatically and stay fairly low. And then we saw an administration come in that really reversed a lot of those protections, and more than even reversing those protections, just has not invested in enforcing those protections. And we have seen 3 years consistently of record high deforestation and the fires associated with deforestation in the Amazon, which I think is both a cautionary tale and also in a weird way kind of an optimistic tale, because I think when we've done the work of putting protections in place and they're being enforced and deforestation rates are really low, or pollution rates are really low, or whatever, we tend to get complacent about that success and just think, well, that just happens, right? That just is the status quo. And to see that reversed, I think drives home just how much power we do have to have an influence, that it is a conscious choice, and we do have the power to make a huge difference between record high and record low deforestation rates in Brazil.
Yeah.
Yuki's got a question in the chat. Hi, Yuki. Good morning. How do oceans fit into your models of carbon sequestration? And I would say in terms of our models, we don't do a lot of ocean modeling per se. Our neighbors down the street, Woods Hole Oceanographic Institution, do a lot of that. And it's really amazing if you kind of take the work of the two institutions and map it. We pretty much have the whole globe covered with only a little bit of overlap in kind of rivers and coastal systems. It's pretty cool. But just broadly speaking, I mentioned that forests and land-based ecosystems absorb about a quarter to a third of human greenhouse gas emissions. Oceans do something similar. So together, natural systems, plant life and life in the oceans, and plant life on land together absorb about 55% of human greenhouse gas emissions every year. And then they turn that around and they pump out about half of, or oceans pump out about half of the oxygen in our atmosphere. So clearly, oceans are a critically important part of this. That's not our particular expertise at Woodwell Climate Research Center. And I would also say, I think oceans as a climate solution that we can manipulate or ramp up face greater challenges than land-based ecosystems, right? We need to be protecting and restoring coastal and ocean ecosystems. but it's not as simple, relatively simple as go plant trees, right? We can plant trees and we can count the amount of carbon there and work to figure out how to boost plant production in the oceans and do that in a way that would actually get that carbon then down to the deep sea and out of circulation. That's still very much an open question. And I think it's an area of increasing interest, but we don't have an answer for how we would do that we could deploy today in the way that we have answers right now that we can deploy on land about forest protection and ecosystem restoration.
Heather, are there technologies under development that you're excited about, that you think have tremendous potential that you'd love to see come to fruition sooner as opposed to later?
Oh gosh. Total cop-out answer. Yeah, all of them. I mean, I'm not saying like down with the tech and we don't need it and we don't want it. We need and want all of it. All we're saying is we can't do that to the exclusion of the nature-based solutions as well, right? So, more efficient solar panels that can do the same with fewer materials and give us more energy, bring it on. Better batteries, updated grid, electric vehicles at scale. Yeah, all of these things I think are critically important. I think one of the technologies that is a real conundrum in my mind is the direct air capture, this idea of essentially big fans that will suck carbon out of the atmosphere. We know from the modeling that we need and will need more carbon capture than we can do with nature-based solutions alone. So we're going to need some sort of technological assistance there. And yet at this point, those technologies are still very nascent and they're incredibly energy hungry. So they create a conundrum where we're going to need to produce even more energy in order to power those machines to pull carbon dioxide out of the atmosphere. And so that's one where I think there's just a real conundrum. We need a lot of very thoughtful and really, for lack of a better word, like we need some really, really smart people and also really, really thoughtful people figuring out how we do technological carbon capture and storage.
Well, if there are no more questions, I'm going to close the event and thank Heather for an amazing presentation. Very informative. I learned a lot. I'm sure everybody did. Have a wonderful rest of your day and enjoy the rain.
Yeah, stay safe and as dry as you can.
Thank you, everybody.
Thanks for having me.